Excellent. Thank you very much. Thank you for the introduction. My name is Agnes Kóspál. I'm from Konkoly Observatory in Budapest, Hungary, and I'm here on behalf of my collaborators, Fischer, Lynne, Hillenbrand, Greg Herczeg, Johnstone, and Mike Dunham. Except for Mike, all of us are here, so please come and talk to us afterward. So we live in the era of time domain astronomy, and young stars are variable. Their variability may be traced back to different physical processes, but the most important and most interesting for us is the variability of the disk-to-star accretion rate. And not only because this will determine how the star is being built up, but also because the accretion variability affects the disk, and within it, the planet-forming material. 10 years ago, at the time of Protostars and Planet 6, there was a chapter and a talk about episodic accretion. So we thought that it is time to have a look at how the field of accretion variability developed since then. And indeed, looking at the posters presented here during this conference, I indeed saw many, many very interesting posters directly relevant to this topic. But I'm not going to talk about them. I'm going to talk about what we wrote in our chapter. So to give you an overview of what I'm going to talk about in the coming 33 minutes, I will focus on accretion variability and what we can learn from it. Young stars are variable, both photometrically and spectroscopically. And they are variable over very different timescales, from the hour to the century. And they are variable at very different amplitudes, from the barely detectable up to or even over 6 magnitudes. The most dramatic events are the accretion outbursts. And I'm going to talk a little bit about the utility or futility of their classification. But there are also less dramatic smaller bursts and stochastic fluctuations. So we need to study a whole range of phenomena to be able to understand how stars gain their mass. I will talk a little bit about how to diagnose accretion and about our current understanding of protostellar luminosities. I will show how diverse light curves and spectra can be, which of course complicates classification. And now we have more and more data at mid-infrared and even millimeter wavelengths about variability. And it's still an open question whether the physical processes behind those phenomena are similar or distinct from what we observe at optical wavelengths, for example. And at the end, I will list some unresolved issues, and I will suggest some best practices and some methods we think would be valuable to tackle these issues. So as an introduction, young stars are variable, and their variability may be related to geometrical effects, like the rotation of a spotted star and the accretion columns. It can be due to changing circumstellar extinction, and also variable accretion, and I will focus on this in the remaining part of my talk. But I have to remind everyone that observationally, it is not always easy to distinguish between the signatures of these different processes. Accretion rate varies throughout the Primient sequence evolution. So class 0, class 1, and class 2 objects are all variable. Accretion bursts are the most important for disk evolution and planet formation because they have long-lasting effects on the disk. For example, they can affect the disk chemistry. They can even affect the forming star, for example, its radius. Small variability may be less significant, but it is still important to understand the underlying physics, for example, in the inner disk and in the mass flow from the disk onto the star. There are many open questions in this field. For example, what is the role of variable accretion in building stellar mass and determining the observed properties of protostars? Do all stars experience large amplitude accretion outbursts as they form, or do these require special circumstances? What triggers the large accretion events like the one I'm showing here as an example? And what switches them off or temporarily stops them? Again, for which this light curve is a nice example. And how can variability such as this used to evaluate the instabilities that lead to the bursts? And how well are we measuring accretion luminosity from monochromatic observations, such as the light curve I'm showing here, which was taken in one single filter? And how does variability influence chemical and mineralogical processes in the disk that affect the formation of planets? To set the scene, let's consider this series of figures. On the left, I'm showing an object undergoing magnetospheric accretion at a quite modest rate. If you look at the spectral energy distribution of such an object from the UV to the near infrared, so let's say from 0.3 to 2.5 micron, you will see that the acidity is dominated mostly by the stellar photosphere, and only at the shortest wavelengths where you have some contribution from the accretion hotspot and the hottest part of the accretion column. Now, if you start increasing the accretion rate, then the material may cross the corrotation radius or the magnetospheric truncation radius, and you start forming a viscose accretion disk that will dominate at optical and near-infrared wavelengths. And if you increase the accretion even more, then what you will see is that you may crush the stellar magnetosphere, and you may form an accretion disk that will extend down to the stellar surface. And the acidity of such an object will be dominated by this viscose accretion disk, and you will not see the stellar photosphere anymore. And this is what we think happens in FURI objects. So to summarize this, magnetospheric accretion is best observed at optical and ultraviolet wavelengths, and you can model either the continuum excess emission or use some proxy emission line diagnostics to measure the accretion rate. And then you have the passively heated dust disk with a certain dust temperature distribution, and for low accretion rates, the reprocessing of the starlight at the disk surface will dominate over the energy released locally. And then you have the viscosely heated gas disk. At high enough accretion rates, you crush the magnetosphere, you form this viscose accretion disk, and its luminosity will correlate with the accretion rate. So all these components are plotted here except one, which is the envelope emission. That's very useful for embedded protostars because envelopes are large dust reservoirs that act as bolometers. The brighter your envelope, the larger the accretion rate at the center. And you can use the radiative transfer modeling to infer the accretion rate. So to recap this, you can measure changes in the accretion rate through a variety of diagnostics. Some of these, especially in the UV optical near-infrared, are direct diagnostics, but you can also use indirect diagnostics in the mid to far infrared and the millimeter. So if you want to understand the accumulation of stellar mass and the role of variable mass accretion history in that process, what physical parameters need to be constrained? Well, the luminosity of a protostellar system is the sum of the photospheric luminosity and the accretion luminosity, and the accretion luminosity depends on the stellar mass, accretion rate, and the stellar radius. The ratio of the stellar mass to stellar radius is typically known. It doesn't really change that much with time, so obviously accretion rate is a key parameter. But we have to keep in mind that the disk to star accretion rate is not necessarily the same as the accretion rate within the disk. For the latter, we actually don't have very good observational constraints. There are some other disk parameters that may be important, like the disk mass or disk radius, which are important for understanding the mass reservoir that is available for accretion. And to measure or constrain these, long wavelengths and spatially resolved observations are very important, such as the one I'm showing here as an example. We need to know whether the disk can efficiently process the accreting material, because if there is, for example, a mismatch between the envelope infall and the disk accretion, this may lead to instabilities and episodic accretion events. Time, of course, is a key parameter. So to constrain that, you can either follow the distribution of accretion properties as a function of estimated population age, so do a kind of a statistical study, or you can observe variable accretion in action, either by monitoring the hourly, daily, or weekly accretion variability of an object, or by following the evolution from quiescence to outburst and back to quiescence of individual young eruptive stars. So clearly we need to constrain parameters beyond instantaneous measurements of presumed steady state or time average accretion rates. We need to measure burst and outburst amplitudes, peak accretion rates, durations, repeat cadences, but most importantly, the integral of m dot dt per event for all events. We are not overly ambitious, are we? Well, we need to obtain detailed light curves, including the rise and the decay, and ideally spectroscopic sampling at key phases as well. Spectra, like the ones I'm showing here as an example, help us to understand outburst physics, constrain disk temperature, measure accretion rate, constrain the disk geometry, and even learn something about the wind properties. So, what do we know about the luminosities of protostars and how do we interpret them? Back in the 1990s, we thought that in a statistical sense, protostars are underluminous compared to expectations. I can explain this in very simple terms. If you want to form a 1 solar mass star in 100,000 years, you will have an average accretion rate of 10 to the minus 5 solar masses per year. And then you can calculate the luminosity of such object, and you will get something like 50 solar luminosities. But actually, the measured average protostar luminosities in Taurus, for example, is only about 1 solar luminosity. This is illustrated here in this graph, where I'm plotting the bolometric luminosity as a function of bolometric temperature. This latter is used as a proxy for age. And you can see that the observed dots are all below these model predictions. So there are two possible resolutions proposed for this. Either star formation timescales are longer, or accretion is episodic, which means that longer periods of slow accretion are punctuated by short bursts of rapid accretion. This means that you increase the average m dot, but the objects would typically be observed in the low accretion state. Now, we know that, mainly thanks to Fischer, we know that protostar lifetimes are actually longer than previously thought, and also extinction correction increased a little bit the observed mean luminosities. So now we think that the discrepancy between the expectations and the observations are only a factor of 2 to 10 instead of a factor of 50. So now we think that that problem, and this is called, or this used to be called the luminosity problem. The problem is not that protostar luminosities are uniformly too small. The problem is more that they span a huge range. There's a spread of 3 to 4 orders of magnitude, both at younger and older evolutionary stages. And we know that models with constant accretion rate cannot reproduce the observed distribution of protostar luminosities. But models that include episodic accretion, like the one here, can. And then here you can see such an ensemble of models with the grayscale, and yeah, they cover basically the whole range that the observations also cover. So this is one possibility, but there are also other models in the literature that, for example, include a smoothly decreasing accretion rate, and then a range of accretions basically to form various stars with various masses. And with these kind of models, you can also reproduce the observed spread, which I'm plotting here as a function of envelope mass, again, used as a proxy for time. And these models don't need episodic accretion. So you may wonder, so is accretion episodic or not? Well, models should not be taken as evidence that episodic accretion does not happen at all, or the stellar growth is dominated by smooth accretion rather than large outbursts. I think what the take-home message should be here is that by themselves, the observed protostellar luminosities do not definitely distinguish among the different possible scenarios. So possible scenarios are either short-term, large amplitude stochastic variability, including bursts, or long-term, small amplitude secular variability, or a mixture of both. And we have to keep in mind that there is substantial observational evidence for accretion variability, both the routine type and the bursty type, and both in protostars and in pre-main sequence stars. So let's stop here for a moment and let's clarify or define some of the concepts and expressions I've been using in my talk. So by routine variability, I mean changes that are typically less than 1 to 2 magnitude. They are often accompanied by changes in the emission line morphology and strength. This is typically observed at optical near-infrared wavelengths on timescales of days to weeks, basically. And this can be quasi-periodic or stochastic, can include short accretion flares, even extinction dips, and this is basically what a normal classical T-Tauri star does. Bursts, on the other hand, are distinct, discrete brightness increases, typically 1 to 2.5 magnitude in amplitude, and a few weeks to a few months in duration. And the outbursts are the largest brightness increases, typically 2.5 to 6 magnitudes, taking a month to years to develop, with a duration of several years or even several decades. And phenomena that correlate more or less with these concepts are these categories. EX loopy events, sometimes called XORs, have bursts that are a few or several magnitudes large. They last for several months. They are recurrent, and their spectra resemble abnormally actively accreting T-Tauri stars. There are the V1647 Orionis events, which are basically have amplitudes and durations and even spectral characteristics which are in between or a mixture of those of EX loopy and F-Uri events. F-Uri events, sometimes called FURs, are which have the large outbursts, sustained increases in bolometric luminosity. Here we have the viscose accretion disk, which overwhelms anything else in the system. So they have a spectra accordingly. And then we also have FUR candidates where we observed an outburst, a brightness increase, but we lack at the moment the spectroscopic confirmation that this was indeed due to increased accretion. And then there are the FUR-like objects where the spectrum looks like a FUR, but there is no actual outburst observed. Now that we clarified all this, let's have a look again at this graph where I'm plotting the typical variability amplitudes as a typical variability timescales. As I mentioned briefly, there are phenomena which are related to the central star itself, or there are phenomena that only happen in binary systems. There are extinction-related variability. But then the most interesting for us is the accretion-related events. So let me clear up this graph a little bit. So I deleted everything that is not accretion-related. And then let's go from the bottom left. So magnetospheric accretion is what produces the shortest time scale and smallest amplitude variability. You can see an example light curve for that. And then here are the accretion bursters with somewhat a larger amplitude and longer time scale. And then we have the EX loopy outbursts, and I'm going to come back to this topic later. And then the V1647 Orionis objects with multiple eruptions, intermediate duration, mixed spectroscopic properties. Some of these are actually embedded. And this is unfortunately a convenient place to park sources that we cannot put into the other categories. And then here are the FUR outbursts, which are the largest one. But if you look at just these three examples, you can already see that the light curve properties can be very, very different even within this category in terms of brightening length and then a peak duration and then the decay timescale. And there are also some additional phenomena that you can see, for example, like flickering in FU Orionis due to some brightness inhomogenesis in the accretion disk, or some dust condensation events that happened in these two Cygnus sources. And there are even sources which can halt their accretion temporarily and then go back to maximum brightness, like V899 monocerotis. But what is important for FURs and what distinguishes them from any other type of eruptive stars is that they have this viscose accretion disk, which is heated from the inside. So they have a hot midplane with a cooler surface, and that results in absorption features in their spectra. And if you compare that to an EX loopy object in outburst, that is basically a T-Tauri star with a very high accretion rate. So it has a hot disk surface and consequently emission features. And then there is this curious category here, the protostellar outburst, parenthesis infrared. So this means that we observe more and more outbursts or brightness increases at infrared wavelengths. Now we have surveys like the VVV or VVVX or the NEOVISE, which surveys the sky at near-infrared or mid-infrared wavelengths. And you can see, for example, I'm showing here some nice WISE light curves. You can see these brightening events. Unfortunately, many of these are still candidates because we lack the spectroscopic confirmation that these were really due to increased accretion, and this may even stay impossible for the most deeply embedded sources. And this is where I should mention the high-mass protostars, because they spend most of their premium sequence evolution in the embedded phase. And indeed, we can observe mid-infrared or far-infrared brightness increases in them. And sometimes these are accompanied by methanol maser flaring. And then a final interesting category are the objects with quasi-regular accretion brightenings. These are typically moderate amplitude objects, and they are not only repeated, but regular, periodic. So this can be due to some kind of cyclic instability in the disk, or maybe triggered by an orbiting companion. So you see all these different categories. Back at the Protostars and Planet 6, we focused on the two main classes, F-Uri stars, EX-loopy stars. But since then, we know that there are distinct brightening events in young stellar objects that come in a range of amplitudes, durations, and propensities to repeat. So this diversity, I think, defies classification into a small number of well-defined categories, and may better reflect a continuum of properties or empirical measurements. So and also we have to keep in mind that classification is not always consistent. You saw, for example, in the Fure light curves, and I didn't even show the spectra, but some properties vary even within a class. Currently, we have clearly expanding, luckily expanding parameter space, because we have light curves that span longer and longer time periods with better and better cadences. We have ever-increasing survey volumes, and we are expanding the wavelength range where we can study variability as well. So it's a question whether we can still use a classical classification. Is it useful? Can it be done at all? And I think sometimes it doesn't really matter into which box we put a certain object, as long as we clearly describe the observed properties and how we interpret them. And what I'm fairly confident about is that it's still very useful to do in-depth studies of individual objects. And to illustrate how much we can learn just by studying one single star, let's have a look at EX-loopy. You can see here the light curve of EX-loopy going back to the 19th century. So I'm covering more than 130 years of observations here. And you can see that this star can produce both outbursts and bursts. So outbursts happened in 1947, 1955, and 2008. These are typically 4 to 5 magnitude in amplitude, and they typically last for half a year. EX-loopy also produced many, many bursts. So these are 1 to 3 magnitude in amplitude, and they last for a few weeks to a few months. So we can have a look at how the accretion rate changed during these events. And as an example, let's take the outburst, the big outburst that happened in 2008, and the smaller burst that happened in 2022. During the big outburst in 2008, the accretion rate went up by a factor of 40. And you can see here how the acidity of the object changed and how the spectral properties in the near-infrared changed, as opposed to the small burst in 2022, when the accretion rate only went up by a factor of 7 to 10. I calculated how much mass was accreted during these events. This one lasted for half a year. This one lasted for about a month. So I could calculate this integral m dot dt. And I found that during the large outburst in 2008, 12 moon masses of matter was accreted onto the star, while during the small burst, only less than 1 moon mass was accreted. And to put these numbers into context, EX-loopy typically accretes 1 moon mass in quiescence during 1 full year. So this is a significant increase in addition to that. I also calculated how much energy is was released during these events. You can see the numbers in joule here. So to put that into context, this is actually exactly halfway between the energy released in a solar flare and in a supernova explosion. Well, halfway, I mean by if you consider that it's logarithmic. But still, it's a very significant amount of energy, and I'm interested in that because that will determine what kind of changes you can induce in the circumstellar matter. The most interesting effect we saw during the 2008 outburst is the formation of crystalline silicates on the surface of EX-loopy's disk. So what we found during the 2008 outburst is that the temperature was high enough within the inner half AU for the formation of crystalline silicates. The originally amorphous silicate grains were turned into crystalline forsterite. And then later, these features started to be weaker, and longer wavelength forsterite features also appeared. So we were very curious what this system would look like now, 15 years after the large outburst. And this is what we had a look at with the GWST, and you can see that the 10-micron silicate feature is completely amorphous now, but there are still visible crystalline features at longer wavelengths. So this means that the crystals that were formed in the 2008 outburst started moving away from the star to more far away, colder disk regions. And by now, they reached the snow line. They are located at about 3 AU. So it is very interesting to think that these crystalline grains are probably growing ice mantles right now, and they're busy forming icy planetesimals and comets. And if you consider that, we also detected lots of different molecular features. You have everything to form planets and planetary atmospheres and maybe even life eventually in this system. I could keep talking about EX loop until midnight, but let's move on to another interesting topic. Let's go back to fjords a little bit. Fjord outbursts are long-lived, so it is very well possible that we miss the brightening of an event and we only observe it, only detect it during the high state or even afterwards. We may completely miss a fjord outburst. How can we recognize these kind of objects? Now, if they are still in the high state, then of course we can look for spectra indicative of these viscose accretion disks I explained earlier. For example, by checking if the effective temperature that you determine from their spectra, if they have a wavelength dependence or if the line profiles are consistent with disk rotation. You can look for special chemical tracers because, for example, in the high state, the water snow line is much farther in these systems than in a quiescent system. And then because of that, you may sublimate lots of different molecules that are normally in the ice phase, and then you may see, for example, increased abundances for complex organic molecules. You can also look at the spatial distribution of certain molecules, and they may show special features that you can recognize as signatures of accretion outbursts. But you have to keep in mind that amplitudes and timescales of chemical changes vary with molecule, from molecule to molecule. Some are more useful, some are less useful to trace these effects. Or you can also look at the variability of outflow ejection, because of course variable accretion should be accompanied by variable ejection, and this can be observed, for example, as clumpy structures in outflows and jets. Unfortunately, the direct link between variable accretion and variable ejection is mostly hypothetical, but there are some nice examples where we could directly link these two effects in certain objects. And this is also very useful to estimate, for example, the repeat timescales, the repeat cadences of outbursts. So there is a potential for identifying outburst mechanisms through a quantitative analysis of their amplitudes, lifetimes, and for those that repeat, their cadences. For example, the physical conditions in the disk and the processes responsible for the unstable flow determine the timescale of the accretion variability and whether it is episodic, periodic, or stochastic. For example, if you trigger the outburst in the inner disk, you will have a shorter time scale. If you trigger it farther out, you will have a longer time scale. The ability of the process to extract energy and angular momentum from the disk will determine the amplitude of the variability. So what we need, basically, is a time-dependent evidence for changing conditions in the disk. Here I'm showing an example for a very nice observational fact, which is that certain fjords start brightening earlier in the infrared than at optical wavelengths. And from this, we can infer that in these objects, probably there is some kind of invert propagating instability at work. But eventually, again, important message, I think, it is unlikely that we can unambiguously constrain the variability mechanism just by looking at light curves only. And this is where observational constraints for the spatial and velocity structure of disks and envelopes come in handy. For disk instability, for example, you need to stop the material from falling continuously on the star. And then once you accumulated enough material, you need to release it quickly onto the star. And then you need to replenish the disk afterwards so you can repeat it. So this means that you should have a mismatch between the envelope inflow rate and the disk accretion rate. And indeed, we managed to measure such a mismatch in one young eruptive star V346 Normae. Using ALMA, we could measure the velocity profile of the circumstellar material, and we found a Keplerian disk in the inner part and the pseudo disk in the outer part, which shows a combination of infall and rotation. So that's how we could measure these properties. There are still some remaining open questions. For example, why are fewer disks more massive and smaller than other YSO accretion disks? Here I'm showing measured disk masses as a function of characteristic disk radii, and you can see that fjords plotted with the yellow and green are typically more massive and smaller than the disks of normal class 1 and class 2 objects plotted with blue and black. So this means that fjord disks are somehow special, but are they special because of the outburst, or they are outbursting because they are special to begin with? So it's a question whether fjords are really born different and follow a different evolutionary path, or any disk can become outbursting and then the outburst will make them special. To be able to answer this question would be very important to know, or to get a step closer to know whether whether all YSOs go through fjord eruptions. There is still the true rate of fjord outbursts, which is very poorly constrained. So if you do these kind of statistical studies, you look at light curves in the optical, you will find that they should repeat every 100,000 years. If you do the same in the mid-infrared, you will find a different number every 1,000 years. So from this, you may conclude that younger protostars have a higher frequency of outbursts, which kind of makes sense because at that time you still have a replenishment from the envelope. But these rates are very uncertain because you need to know the accurate number of outbursts, and you need to know the accurate number of total young stellar objects. And there are several problems in determining both the numerator and the denominator. So in summary, since the brightening of FURI over 85 years ago, we have made some progress in linking observational phenomena to the underlying physical mechanisms, but there is still much to learn. The integral of m dot dt is a critical parameter in knowing how much mass was accreted. We must clearly look beyond the protostellar luminosities to make additional progress. Traditional classification schemes are imprecise, and members assigned to a given category display a range of properties. Spectroscopy is essential, both for distinguishing between fjords and other types of eruptive objects, and for verifying that a certain brightening event was indeed due to accretion. So to understand the stellar mass assembly via variable accretion, observers need to monitor individual outbursts, but also undertake a systematic investigation into the full range of accretion variability phenomena. And theorists need to continue to work towards more precise observational diagnostics. So on my last slide, I would like to suggest some best practices for us. Keeping in mind that we are in the era of all-sky photometric monitoring at multiple wavelengths, you may think that now we can discover as many outbursting objects as we want, but that's not true. So if you consider automated techniques for identifying outbursts, they don't always work very well, and the most interesting events may end up in the junk pile. And of course, follow-up is essential because disentangling the physical reason behind a certain brightening event is not trivial at all. So what I would suggest for observers is that multi-wavelength approach is essential, spectroscopic follow-up is essential, spatially resolved observations with interferometry such as ALMA or NOIMA or even via the VLTI is essential. And well, we have to be patient. Sometimes it's worth to wait for more data before making conclusions and publishing papers. For theorists, it is important to constrain and quantify the range of conditions under which episodic accretion happen. And it is important to couple the models with radiative transfer to predict observable quantities. So I think what would be nice is to agree upon a certain set of measurements that both the theorists and the observers can begin to compile, and this will lead to a better understanding. So my time is up, and I'll take questions.
Perfect
Thank you.
timing. Thank you very much for excellent talk. Now the floor is open for questions. So please give your name and affiliation before you ask questions. Let's start with this line.
I'm Valesca Valdivia from Nagoya University, so thank you for the talk. And I have a question concerning the accretion luminosity, because in the expression that you use that there is an efficiency of 100%, so all the gravitational energy is converted into luminosity. But there might be another mechanism, so we don't know, or actually I don't know, if there is any efficiency known and well constrained for the conversion between energy and accretion luminosity.
As far as I know, no, not really. I don't remember reading anything specific about this in the literature. It may depend also on the process, how the material ends up on the disk and on the role of the magnetic field, because, I mean, there's this assumption that in the most intense outbursts, you get rid of basically the magnetic field, and it's not important anymore. But it's uncertain. It's very difficult to get observational constraints on this, and also how the angular momentum is carried away, because you may expect that fjords, for example, should have much more energetic, much more massive outflows, but that's not always the case. So it's not clear that what is the exact relation between how you transport material inwards and outwards. And there are all these details that may be important in this efficiency. So yeah, I think that's something for the modelers maybe to help us out, observers.
Okay, thank you.
Let's have a question from the other side.
Gary Fuller, University of Manchester. A very interesting talk, thank you. But you didn't mention radio or X-ray variability, and I wondered how you felt about those as probes of this kind of event.
Yeah, that's a very important thing, especially because I'm personally very interested in the outburst effect on the disk chemistry. And of course, whenever you ask an astrochemist to make a chemical model of your disk, their first question will be, okay, so what's the UV flux, what's the soft X-ray flux, what's the hard X-ray flux? And I'm not an X-ray astronomer, so I typically don't know the answer to these, but there are very nice papers in the literature. People have been observing outbursts and bursts in the X-rays, so that there are some constraints on this as well in the literature.
And also in the radio.
Yeah, let's have a question from the back.
Okay.
Left.
Hi, Leire Beitia from Universidad Complutense de Madrid. I'm curious about the part that you mentioned, these crystalline silicates. So how can you be so sure that they just migrated to the inner interior of the disk instead of being destroyed or reprocessed?
Our assumption, our evidence, I think, is basically that we started monitoring the spectral features. So already with Spitzer, we could take multiple spectra, and then what we started seeing is that the 10-micron forced right features decreased in strength, and then the longer wavelength forced right features started being stronger. And then we could continue the monitoring from the ground only at 10 micron, and then we already saw that a year or half a year afterwards, the 10 micron feature was completely amorphous, and then we lagged instrumentation to check the longer wavelength part. And then now with James Webb, we actually still see the long wavelength features. And then it would be nice, of course, to keep monitoring it. And then basically what happened is that first the shorter wavelength features appeared, for which you need warm crystals, and later the long wavelength feature appeared, for which you need cold crystals. And then, so, I mean, you can destroy the warm crystals somehow, but then you would need to explain how you can produce cold crystals, and I have no answer to that. So the easiest answer was that, yeah, you don't need to create them. They were made in the inner disk, and then they were just being transported to colder regions. And then you can calculate how much velocity you need for that, and it's just a few kilometers per second. So it's completely plausible to think that maybe the disk wind dragged them farther away. Thank you.
One more question from this line.
Hi, Abigail Frost from ESO Chile. Thanks for a really nice talk. I was wondering if you could comment on the role of companions in the accretion process and how whether the presence of a companion, or wide or close, can help to, dynamically affect material that's involved in accretion. And yeah, just any comment you would have on that would be great. Thanks.
Well, that's a whole field of science because of the different spatial scales and time scales involved in these processes. So I know that if you have a very, very close companion and there's a circumbinary disk, then if your system is an eccentric binary, for example, then the accretion process may actually be modulated with the same period as the orbital period, and then you have these pulses of accretion onto the system. And then if you have something that orbits within the disk, there were models in the literature earlier that you may basically make a perturbation wherever you are orbiting, and then you can start this ionization front that way if you have a high enough density perturbation. And then if you have an even farther companion, then there are, I think, studies into how that may perturb the disk by a flyby, and then that eventually may propagate inwards, and then you will have the increased accretion. But it's very difficult to really link objects with certain accretion events. But for example, there are objects where, for example, Z Canis Majoris is such a system, I think, or maybe Fu Ori might be such a system where we know of companions that may possibly have triggered the current outbursts, or maybe they triggered something earlier, or maybe they will trigger something in the future.
Great, thank you.
Okay, let's have a question over there. Yeah.
Yishen Zhang from University of Virginia. So you mentioned briefly about the outflow variability and the accretion variability. So could you elaborate a little bit on this? Especially, I wonder if there's like a connection of the ejection rate and the accretion rate during the outburst.
Well, I'm no expert on this field, so whatever I know is just I read a couple of papers where people try to link. Basically, you can do integral field spectroscopy, and then you can study the spatial and velocity structure of these jets and outflows, and then if your source is not very embedded, then you can have from archives or from different sky surveys, you can try to construct its light curve, and then you can just try to correlate the two. But of course, you would need a very lucky kind of a good geometry to be able to do this because of the different time scales. I mean, light curves are typically available for the past few years, and the dynamical time scales that you derive from jets and outflows are typically much longer. So you need a lucky situation where you have a time period and a spatial range that you can both study in enough detail that you can really link this. And there are maybe 2 or 3 papers in the literature where people could do this. For fjords, this is really, really difficult, typically because fjords are distant. There is one in Taurus, a couple of them in Orion, 3 times more distant, and then the rest is typically around 1 kiloparsec or even farther away, and there is no way to link their light curves to any features we observed because those are thousands or even 10,000s of years old.
Thank you.
Okay, question from the right side. Yeah.
Hi, this is Nagayoshi Ohashi from Taiwan. So I was curious, or actually a bit confused about the evidence about between the mismatch between the inflow rate in the envelope and to that star. So what they are saying is that just there's a outflow, inflowing envelope, and the inner side is a Keplerian, so the outer part is a higher accretion rate, and the inner part is a lower accretion rate. Is this what you are saying?
Yes, yes. So basically, this was a very lucky situation that this object stopped accreting for a while. If you check its light curve, there's a minimum that lasted for about a year, and we could estimate an upper limit for the accretion rate. So we assume that that's an upper limit for the quiescent accretion rate. So that is what would be transferred in quiescence from the disk onto the star, and then we could measure basically from this velocity profile for a pseudodisk. There's an analytical formula that you can use to convert that to an inflow rate, and what we found is that the inflow, so the material that the disk gets from the pseudodisk, let's say, is much more than what is transferred onto the star in quiescence.
Okay.
And that is the mismatch. So that means that there should be accumulation, and then that accumulated material can then quickly fall onto the star and cause the outburst.
Okay. Then there are not only this case. There are several such observations, including the latest EDISC observations. We are measuring the inflow rate within the envelope, and we can also measure the mass accretion rate to the star, because we are measuring stellar mass as well. And also we can look at the like a black gamma to measure the mass accretion rate to the star as well, and we can see that such a mismatch.
Yes,
so not
yes,
only
yes.
this case.
Yes,
Okay.
thank you. Yes, I've seen. I get the inspiration for this study from those papers, and but this is the unknown fjord where we could do this. So that was lucky discovery.
We are running out of time, so this will be the last question from here.
Okay, Andrei Zella from Rice University. I have a question and a comment. The question was already asked in part, which is radio variability in the radio. So I wonder whether you can elaborate a bit more what monitoring the radio can bring, what other diagnostics you can have. My comment is about the radius of FU Orionis compared to radius of class 1 and class 2 disks. And although it's true that some class 2 disks are very large, if you look at the collection of disks, for example, in our chapter 12 and also chapter 15, the vast majority of class 2 disks are actually pretty small. And so I don't think, so you're missing a lot of points for your class 2 on the small side. So I don't think there is actually a mismatch there, because, I mean, the disk you have on the large disk are really a minority of class 2 disks.
Yes, so to comment on this, I was trying to be very careful with what I'm plotting here, because this is an issue in this field that sometimes methods, wavelengths, models are different, and then you're trying to compare apples with pears. So what I'm plotting here is observations that were taken with similar instruments at similar wavelengths and modeled in the same way. So with radiative transfer model, with the same parametrization, so I could really put points where RC means the same for all of them. So I didn't, that's why I discarded lots of studies, because they were doing something different, and I didn't want to redo those things. So that's why there are a few points here. So this might be biased, so hopefully within the in the future, I may be able to add more points as more observations will be available, and more objects will be modeled in the same way. Because, I mean, radiative transfer is important, because if you check these objects, or at least partly in the central part and not an insignificant part, they are optically thick even at longer at these long wavelengths. And then to comment on your remark about the radio variability, I think there's a very good potential in that, and then because in some objects, and there's a good study, very detailed study on FU Orionis itself. I mean, it depends on what you mean by radio. I mean, you can go from the millimeter to centimeter to even decimeter wavelengths, but then you have to keep in mind that you may have not only thermal emission, but also non-thermal emission, and then there are evidences for ionized bubbles in these FURs, so all kinds of interesting phenomena that can be variable as well. It's not an easy task, again, for example, to compare interferometric observations, millimeter observations, because of, you have different instruments, you have baselines, different coverages, different portion of the flux may be filtered out by the interferometer. So it's difficult, but there are the beginnings of such studies.
Let's thank Agnes again.
Thank you.